Okay, so I've gotten several emails from students about Green's theorem, and because I do a few examples. I said there were a few we were going to go through in class, but since I got the emails, I'm just going to make the video here, and then you can watch them whenever you want to go through some of these. This is the one I told you to do at the end of class. I said, given that line integral right there, over the unit rectangle right there, use Green's theorem. And just so we can see it written out, this is Green's theorem for flux, and this is Green's theorem for circulation. So, and just so we are clear, sometimes you are simply told, evaluate that, and you plug it into the appropriate Green's theorem, and you're fine. Other times, like this, deliberately, I'm telling you, evaluate it using both forms of Green's theorem just to see what you get. So for this, we'll start with this formula right here. And essentially what I have to do is, the idea we had said in class, that's a line integral. If we think about the line integral right here, well, I have to break this up into 4 different paths. And then I have to kind of manipulate that. And can I do it? Yes. And is it probably going to take a long time to write all that out? Well, yeah. Green's theorem says, this is the hard thing that I don't want to have to solve. So I'm going to write it as a double integral, which is easier generally to solve. All I have to do is equate the two. And in this case, for flux, it's clear I need p dy. So p has to be 2x squared y. And q, I need q dx. That has to be 3y cubed. Now, I just plug in. And I get, well, let's see. This integral right there, which is p dy minus q dx, is going to equal the double integral of the partial of p, which is 2x squared y dx, plus the partial of q, which is 3y cubed dy. First, I do my differentiation. The partial of this with respect to x will be 4xy, plus the partial of this with respect to y will be 9y squared. Now set up my limits of integration. In this case, that's a unit rectangle. It's the definition of a rectangle. So those are just going to be 0, 1, and 0, 1. And I'm looking for all my markers because they're scattered around. And I get the integral from 0 to 1 and 0 to 1 of 4xy plus 9y squared dA, which is just the first one with respect, oh, I'm sorry, in my limits, in my notes here, I went dx and then dy. So with respect to x first, I get 4x squared over 2, which is 2xy, plus 9y squared x. Evaluated from 1 to 0, dy. Plugging in the 0 doesn't actually matter. I left off my square right there. Yep, good. And so I will get, when I plug in 1, 2 times y, the x squared is just 1, plus 9y squared, again the x is just 1, dy. Integrate again with respect to y, and I get y squared plus 3y cubed. Evaluated from 1 to 0. Again, the 0 doesn't matter, and I get 1 plus 3, which is 4. And I'm done. And again, if you were just told, evaluate that line integral, I plugged it into Green's theorem, I'm done. The solution is 4. But for this, we want to use both theorems. So now we'll do circulation. And I'm going to deliberately leave the p and the q right there from that theorem so we can see this, because this is important. I need my p and my q again. But now for circulation, my line integral is p dx plus q dy, which means the thing multiplied by dy, 2x squared y, is actually q here. And I need p dx, the thing multiplied by dx, is 3y cubed. The fundamental difference here being the p and the q flip. I think Audrey in class had said, will I always have the same P and the same Q? No. Depends on which form of greens you actually use, they flip because of the setup for this. And that's what I was kind of saying in class. I'm saying yes, no, but no. Because it varies based off of which one you actually use. But now, I'm not going to bother to solve this all out, but just to write it out, I would get the integral over d of the partial of q, which is 2x squared y, with respect to x, minus the partial of p, which is 3y cubed, with respect to y, dA. Now I would just need to set up my limits and all that, but it's pretty clear. Before I simplify this out, I can use the exact same setup here, because it's a unit rectangle, not a big deal. Solve it all out, and I think the other question that came up in class is, if I use different Green's theorems, will I get different answers? If you solve this out, you get 4, the same answer, which makes total sense, because again, all I'm doing is solving this integral right here. Regardless of which theorem I plug it into, which form of Green's I plug into, I have to get the same answer, because it's the same integral. How I choose to write it is up to me. All I have to know is there's 2 forms of Green's theorem, one for flux and one for circulation. They will result in the same answer. I just have to figure out, okay, if I'm going to use flux, this is the P I use and this is the Q I use. If I'm going to use circulation, this is the P I use, this is the Q I use, and then I plug in and solve. In theory, could you just say always use this one? Yes, but be aware, and again, you see it on the problem that I gave you to do. Sometimes you are told, use both forms of Green's, essentially to make sure you're doing it right by checking both ways and making sure both forms of Green's give you the same answer. But they will give you the same answer, so in theory, you could only use one. One more example, the one we did at the beginning, that I mentioned at the beginning of class, the reasoning behind why we actually used this Green's thing, and I can't believe I just erased the formula that we were going to use. Okay, well let's see, wrong page, notes, here we go. So here, suppose I have the one we did in class, f is equal to y squared 3xy, there's my vector field. I need, for this one, oh, I'm sorry, I'm trying to write out what we had in class. And that's why I have to look at several pages of notes. We were given this line integral to solve. And the region we were integrating over was the upper unit disk right here. Oriented counterclockwise to make sure it was positive. And again, that line integral may be a challenge to solve. So I have to decide, well, maybe I can solve it by writing a double integral. Clearly for this one, or at least we'll say the way we set it up in class, we set it up where we said this was P and that was Q right there. So now I have the line integral of P dx plus Q dy, which is now equal to the double integral of dq dx minus dp dy. Now, for this setup right here, well, I know what my P is and my Q is. Now I just need to plug into this. So now let's see. That's the double integral of dq, which is 3xy, with respect to x, minus dp, which is y squared, with respect to y, dA. And then I get, well, let's see, the double integral. Partial of that with respect to x is 3y, minus the partial of this with respect to y is 2y dA, which actually simplifies 3 minus 2y to y dA. Now the only problem is I have to find my limits here. Here, because it's not a rectangle, it's a half circle, they're a little bit more challenging, but all of you, I'm sure, can do it. So I will shortcut writing all that out, and I'm going to integrate with respect to y first and then x. On the upper half unit disk, the x's go from -1 to 1. The y's go from 0 to the square root of 1 minus x squared. Now just solve the integral. I'm going to leave that to you because all of you can do that, and you should get 2/3 when you work it all out. But again, in reference to the question that Audrey had asked, in this case, I honestly can't remember how we formulated the question, but I think I gave you the line integral like this, so then we said, okay, I'm going to define the vector field as this vector field to line them up P and Q. Then, once I had this form, P dx plus Q dy, that then dictates which form of greens I have to use. In this case, it would be this one. Then I just plug in the P and the Q where they go and solve. If I had maybe called this one Q and this one P, and really just flipped these or something, would it have been different? Or put another way, maybe, if I was just given that line integral, if I didn't bother to do that, could I have maybe, I mean, the order of this is the sum. I could just kind of flip that around. How is this any different from the line integral of 3xy dy plus y squared dx? If I looked at this, then my resulting f would be 3xy y squared. And so again, the point being, there's different ways to write these things. Understand the theorem you're using, equate it however you choose to equate it. You'll notice I'm writing the formula out every time. Okay, there's my P, there's my Q. This one results in this form of greens, the double integral. Now I plug in, then the rest is just the integration that I know. As long as you do that, it should be fine. And again, generally speaking, this is how you're going to use greens from a problem-solving perspective. You're going to be given a line integral that is challenging to solve, so you rewrite it as a double integral, which is easier. You could, I suppose, if you were so inclined, try to start here and go backwards to there, but that might be more of a challenge. And again, it's not really how we use greens. It's generally used this way. Green found a way to solve this using something easier. If you need more examples of this, let me know, and I'll just make more videos. It's not a problem.